Hey, welcome back. We are here with our third deep dive stream in the linear regression and gradient descent. In this recording, we're going to try to extend what we have with our gradient that we calculated last time on a simple linear regression case with just one predictor to multiple linear regression with several predictors. Really just going to rely on some matrix notation. So let's go ahead and dive right into it. Okay, so just a quick refresher on what we had done last time was we have our mean square error loss function here, L. We can calculate its gradient, which is the partial derivatives with respect to all of the variables b and w here. And that gradient is the vector that's going to point you in the direction of steepest increase. We went through all the details of the calculation, found the partial of L with respect to w is this, and the partial of L with respect to b is that. And so using those partial derivatives, we could update our guesses for our parameters by stepping in that direction, and that'll help us decrease our loss, or I guess stepping in the opposite of that direction will help us decrease that loss. Now, what we have here is something that works for simple linear regression. You see our model prediction b plus wxi right here is just taking in that one predictor, that one x. We want to be able to deal with multiple linear regression, so I want to be able to put in an x1, an x2, and an x3 different features there, right? So what we're going to do is we're going to set this up to extend to multiple linear regression by first using matrix notation to kind of re-notate and re-express everything we just have. That way, we only need to do this once in a general case for vectors and matrices, and then it doesn't matter really what the length of the vector or matrix is. The algebra and calculus will all play out to be essentially the same. So first things first here is I want to go ahead and vectorize some of the concepts we had before. So I'll just say this strategy or goal here is to vectorize this stuff. Okay. And I want to be careful with some of my subscripts and superscripts. So let's write this out here. So for the, let's say, ith case of data. So in the ith row of our data set, we can write that y of xi is equal to b plus wxi. Okay, so that's how I'm expressing just the simple. We're still going to start with the simple linear regression, but we want to be able to write this expression in a vector notation. So this is for the ith case of data. So what I mean by this is if you think about like row 1 in our data set, then we would have y of x1, so the observed value, so like the house price of the first house we're looking at is equal to b plus some value for w, and then its feature value x1. I think the opening example I've used several times was just things like square footage of your house. So the second row, that would be y x2, b plus wx2. And so in row n, if we have n pieces of data, y of xn equals b plus wxn. So that's what we're looking at for that. So in terms of writing this and looking at our data set, I'll say y of capital X then is equal to, I'm going to have a column of ones here for the constant or the intercept or bias term b, and then I've got my feature values for my data set. So that's x1, that's the x feature in the first row, x2, x3, xn, and then times our b and w vector. B and W vector here, right? So we can write this in matrix notation as that product then, right? So what I'm saying here is we're just getting to write this as y of capital X is just equal to capital X dot W, where that is my vector here. So this is my capital X. This is my W vector. Notice the dimensions here. This is n by 2 rows and columns, and then 2 rows and 1 column, 2 by 1. Looking at the dimensions is something we can keep track of if we really want to be detailed as we continue to progress through this. So there we go. So we've taken our simple linear regression case and looked at our data set and wrote this out in kind of a matrix form. So that's nice. Okay. Cool. Some other linear algebra properties I want to refresh ourselves on before we, I guess, go any further with this and try to think about finding a gradient using vector calculus is what the dot product is, and that if I have two vectors, it's going to give you a scalar. So if I have a vector A, it's got A1 and A2, and then I have a vector B that has vectors B1 and B2. Then if I do A transpose dot B, so that row times the column vector there, that's just going to be A1 times B1 plus A2 times B2. That is a scalar. And so we can also write this summation here on the right-hand side, this dot product, right? This is the sum of AI times BI, as I goes from 1 to 2 in this case. So that's pretty nice. Cool. All right, so I'm bringing back that dot product because I want us to think about our loss function, or mean square error loss function that we looked at before. So our loss function, mean square error, L is equal to 1 over n times the sum as I goes from 1 to n. And we have b plus wxi here minus the observed value for that case, quantity squared. And the previous streams and dies, we wrote this down in maybe the other order, but for the difference, we're squaring it, so that's a-okay for us here. And what I want us to see is this squaring term right here. If we actually sort of expand this out, we can kind of reverse this process and go from a summation to a dot product. So this is equal to 1 over n times the sum as I goes from 1 to n of b plus wxi minus yi times b plus wxi minus yi. Okay, looks good. And what we have above here, if we look at what these b plus wxi's are, right, that's essentially just my x times w terms here and here. And taken holistically together, x dot w, right? So this is equal to 1 over n, and this summation here is just going to end up being x dot w minus y transpose times x dot w minus y, right? So this dot product between these two vectors, these two items right here are just vectors right there. The dot product replaces the summation. The summation. Oh no, my stylus. Low battery, possibly. Solutions, possibly. Fixed it. The old reboot. All right, let's get back at it. Okay, so the summation of the product of two things, right, can be written if I kind of reverse engineer from here to here, right? The summation of that product, right, is the dot product of two vectors. So I basically take this piece, writing it with that vector notation, x dot w minus y. And this piece right here, I'm taking the product of those two items, right, and adding those together. So that is the dot product of this vector here and that vector there. So the dot product replaces the summation, is what I was writing down in the notes. Replaces the summation. Okay, good. So that's pretty useful so far. So we've taken so what we have so far is setting up our simple linear regression case. Is we know we can write up the goal there of our whole data set, x dot w, right? Secondly, we have our loss function that we know we can write in this faction, x dot w minus y transpose times x dot w minus y. And something else we need to be aware of is that the transpose has something called the sock shoes property. So more refresher. The transpose has the sock shoes property. There's actually, I think, a legitimate name for this property. And I don't really care to look up what it was. Something in the order of some inverse associativity property or whatever. Anywho, sock shoes property. I remember the sock shoes property because that's the description where you put your socks on and then your shoes, and you're going to undo it. You have to go shoes first, then socks second. So if you want to go in the reverse direction, you have to reverse the order of it, right? So what I mean here, if I have the product of AB transpose, if I want to distribute that in, I reverse the order. I go B transpose, then A transpose, right? So that's the sock shoes property. In terms of looking at the transpose we have here, where we have x dot w minus y transpose, right? Think about what that would be. That would be x dot w transpose minus y transpose. So distributing it inside the subtraction isn't going to change that really for anything. But the x dot w transpose means that this is going to be w transpose dot x transpose minus y transpose. And so writing it in that fashion is something that we will do. So if I go back to up here and bring this down, I'm going to say I have 1 over n, and I'm going to rewrite that first term there using this, using the kind of distributing the transpose inside. So instead of x dot w minus y transpose here, I'm going to have w transpose dot x transpose minus y transpose, right? And then let me bring this piece down here, x dot w minus y. Looks good. Okay. So why am I going to do that? Bear with us here, all right? What we're going to do is we're going to go through, we're going to distribute this product out, do a lot of simplification, hopefully, and manipulation, and be able to rewrite our loss function in something that's going to be a little bit easier to work with to get to the gradient. Because remember, at the end of the day, we're going to want to be taking the derivative of this, and the derivative as is would be a little bit hairier than it needs to be. Okay, so let's go ahead and do a few things here. We'll go ahead and distribute. I'm going to take this in a lot of extra steps. You could probably do this in fewer lines, but just to try to make sure we don't make any mistakes. Oh, actually, in terms of this, let me just ignore the 1 over n. That's a constant piece. I'll just write an arrow there. I'm just going to multiply 1 over n at the end of this, but I really just am concerned about with that product. So let's go ahead and do the distributions here. So I'm going to take the W transpose times X transpose, and then multiply that into X dot W minus Y. And then we're going to have minus Y transpose times X dot W minus Y. Okay. So far, so good. So what is this going to be? This is going to be W transpose X transpose, and then now times X dot W. And the dimensions here are going to work out. We could go through and write them out, but we can see, I think obviously, right, that X, the W transpose dot X transpose times X dot W will be just fine. And then what else do I have here? I'm going to have minus W transpose X transpose, and then times a just the Y. Yeah, I have the minus in here already. I had to think about that for a second because I was like, where is this negative going? The negative I already have actually right there. Then minus Y transpose, now distribute this. So Y transpose X dot W. Then we have double negative here, so we'll go plus Y transpose and times Y, vector Y. Very good. Awesome. So let's see here. What do I want to do here? The next step I want to do to make this, you're saying this is looking a little bit more nasty. It is right now, but I'm going to go ahead and rewrite the middle term. The middle term. So let's see here. Let's just write this out. So I've got W transpose X transpose X dot W. And to rewrite the middle term, we're going to go minus, and we're going to sort of reverse that sock shoes property here, right? Where I'm going to have a single transpose on the outside. So if I want to reverse that sock shoes property, then we have to reverse the order in addition to taking the transpose, and the transpose of the transpose is just those vectors itself. So I'm going to have Y transpose dot X dot W, and the X and W no longer have transpose because I factor that out right here. Looks good. And then any other rewriting, not right now. So let's just copy this down. Y transpose dot X dot W plus Y transpose dot Y. Rewrite our middle term there. Okay, cool. And now if we look at our middle term here, let's see, think about what we have going on in this middle term. Remember, Y, the vector Y, is just our observed values. So I don't know who to look at. Sometimes I want to look at the screen. Sometimes I want to look at the camera, but I think that might look kind of weird. So apologies for making this awkward. This is the vector of the observed values. So when you look at your vector of observed values, you take the transpose, that's now a row vector. So this is now a row. And my laptop froze again. Unreal. What we were saying, Y transpose is a row. Okay, now look at the dimensions of X dot W. Remember we said X at the start is an n by 2 matrix and W is a 2 by 1. X at the start, we said this is n by 2 and this is 2 by 1. Well, the product there, those dimensions, n by 2 and a 2 by 1, is going to yield an n by 1. And n by 1 is n rows in a single column. So that's a column vector. So what you have here is when you do x dot w, you get a column vector. So we have a row times a column vector. We have a row dot column vector, and a row dot column, which is what we pointed out earlier on today, row dot column, that is a scalar, right? That's like a summation of those items. So this is a scalar. That is a scalar. It's going to end up being a 1 by 1, right? And so the scalar, or a 1 by 1 transpose, is equal to the same thing. It's still scalar, or it's still 1 by 1, right? 1 by 1 transpose is that same 1 by 1. So what we have here, by taking the transpose here, it's essentially the same thing as it is originally. So I have y transpose dot x dot w transpose. The reason why we wrote it like that is because that is the same thing as what we have right here. So this is the same. These are equal. These are equal, so we can take them and we can go ahead and combine those two middle terms. So we have w transpose dot x transpose dot x dot w minus 2, let's just write it with as it is in white there, 2 times y transpose dot x dot w plus y transpose dot y. This should have a vector. These y transposes need their little vector. That's still a row vector there. Okay, cool. So that's a little bit nice in some sense. So our loss function L, the mean square error loss function L, is equal to 1 over n. That constant would just still be there for hanging out for the ride, times w transpose times x transpose times x dot w minus 2y transpose dot x dot w plus y transpose times y. And I realize I lost a vector hat right here as well. Y transpose times y. Good. Very, very, very cool. Actually, we should be maybe writing this as L is a vector, a function of the vector w. And in this case, w is just the length 2 vector, b, and w with the actual scalar parameters inside of that. Okay. Very, very, very cool. Very cool, right? I'll put a box around this. So that is some very good progress. So we've taken our linear regression problem. We've wrote it in that matrix notation, x dot w. And then now we've taken our mean square error loss function and have written that in terms of x and w as well. And so our next stage is to get the gradient of L of w, which means we would want to differentiate this with respect to w. Well, we can do that. It works out kind of like you might think, where if you were to just treat this not as vectors or matrices, but just think about this as if x was just a regular, if this was a regular function in terms of w, how you might do that. You would need a product rule here. You have essentially a lot of constants here. That is essentially constant with respect to w, so that's 0, and it's not so bad. But because you're doing it in vector form, it handles all of the partials you would need in order, and everything works out nicely. But we had a lot of technical difficulties already with the tablet freezing, so we're just going to stop here today and take it as a win, and I guess we'll pick it up on our next stream next week. Yeah, let's leave calculating the gradient for L to the next stream next week. We'll hope to see you then and hopefully have less technical problems.